Okay. So last time we ended on resistance and resistivity, and we talked about the fact that material and dimensions of a wire determine how much resistance it has, but also the temperature does that. Let's look at this example of change in resistance due to change in temperature. Okay, so here's the equation. The resistance change becomes, you take the original resistance, multiply by the quantity 1 plus alpha delta T, where alpha is the heat coefficient, the temperature coefficient of the material. And then you can calculate that new resistance where your alpha is in this table up here. And here's the example that we're going to use. Excuse me. Resistance of a tungsten filament in the previous example, so we're going to take the resistance from the previous example. We're going to increase the temperature from room temperature to a typical operating temperature of 2850 degrees Celsius. So there's our delta T. We take 2850 minus 20 degrees, put that in for delta T. Look up the alpha for it's tungsten. 4.5 times 10 to the minus 3. And then we plug in the original resistance from the previous example and just calculate. 4.8 ohms. Remember, our original resistance was 0.350 ohms, so heating it up increased it by over a factor of 10. So your resistance can change quite a bit. And how linearly it changes depends on the material as well. It turns out that there is a material that, when it's pure, has a very linear change. It's very easy to predict how much the resistance is going to change over a large temperature change. And that is platinum right here. Platinum has this 3.93 times 10 to the minus 3 alpha, which is, there's a lot of things that are about that. But this one doesn't. This number is constant over a huge range of temperature, going very cold and very hot. And so they actually use platinum for, if you want to make a thermometer that is extremely accurate over a large range, and extremely, you can use this. You essentially use a wire of platinum, and then you heat it up or cool it off. That's your thermometer, and you put a current through it, and then as the resistance changes, the current will change. And then you can actually have a very, very good thermometer. I worked for a company that made these thermometers, and I was just floored at how expensive they can get, hundreds of thousands of dollars. Of course, platinum is expensive, but not that expensive. And but it's the purity of the platinum that makes it very expensive, and also the electronics for measuring a very, very small change in current is also part of the expense, but they call them platinum resistance thermometers. This also, these thermometers that you may have seen before also use, and many thermometers use resistance to measure the heat, a change in resistance to measure, not to measure the heat, to measure the temperature change. And these are included. These use a device called a thermistor that is usually made of silicon, probably a silicon and germanium actually combined, and you can get a change in temperature. Notice that some of these have a positive thing, and some of them have negative. Most of the metals, in fact, all of the real metals, the true metals in this periodic table, have a positive alpha. That means that as they heat up, their temperature, as their temperature increases, their resistance increases. But with these semiconductors, carbon, germanium, silicon, and most semiconductors, it actually goes the other way. As they heat up, their resistance actually goes down. So that's why they have the negative.
So for some crazy reason I want to make a wire out of carbon, it would be better to do hot carbon than cold carbon.
Well, if you're trying to make a very low resistance wire, yeah. But that is kind of the idea. And you can make wires out of carbon. It's not a hard, and people do it all the time. Resistors are often made of carbon. So.
Well, the hotter it is, the less resistance.
That's right. As they heat up, they lose resistance instead of gain resistance. So, we move on now to electrical power and energy. So remember last semester, what did we learn that how are power and energy related? What is the relationship between power and energy from last semester? Right up on the screen if you read it carefully, it tells you right there.
Power equals voltage over amp.
That's not related to
Power
energy.
is energy over a unit of time.
That's right. So power is energy per time, right? So power is to energy as velocity is to distance, right? You can move a distance, but how fast you move that distance is your velocity. And you can have some energy, but how fast you use that energy is your power. So power is how quickly you're using energy. And that's one of the reasons that we can say things like, you know, this scientific device, like the, I think the I can't remember what it's called all of a sudden, but the big laser, the ignition facility, the National Ignition Facility in California, it uses more power than the entire United States does, but only while it's running. It only runs for a few seconds at a time. And so it's not really using that much energy because the time is just not that long, right? So, but for that short time that it is using energy, it uses it in a very, very rapid clip. You need to remind me next time we go to California to visit Grammy that we should go take a tour of the National Ignition Facility.
I thought we determined the last time that they did not give tours.
They do give tours. I've never looked into it really. So they do give tours, and I know the right people. I know people that work out there. Well, of course, your uncle works out there too. So I'm sure we could get a tour.
All right.
You just got to remind me. We probably have to do it beforehand, so we have plenty of time. Anyway, National Ignition Facility, big laser facility. We'll talk about it later in this class. But power is energy over time. In this case, they're calling it potential energy over time because we're talking about circuits, and potential energy is the easiest thing to talk to. We can talk about because it's directly related to voltage by the charge. So if it's potential energy over time in a circuit, power is equal to Q charge times voltage over time. And power also ends up equaling current times voltage because current equals charge over time. So this charge over time in here becomes your current, and you get power equals current times voltage. And this is essentially the Ohm's law version of power. So power equals current times voltage. But you can use Ohm's law to replace current with V over R. And so you get power equals V squared over R if you replace current with V over R. Or you can use Ohm's law to replace voltage with IR, and you get power equals I squared R. And so you get three different versions of power using Ohm's law. P equals current times voltage, P equals voltage squared over resistance, and P equals current squared times resistance. So if you know any two of those things, voltage, current, or resistance, if you know any two of them, you can calculate the power that's being used. Now, this paragraph is fairly important. Each one of these each one of these equations has different implications as to what's going on in the circuit. The power equals I, the current times voltage, is kind of the most, I guess, innocuous ones you could say. But it's just it just gives you an idea of the because it's just current times voltage. It just gives you a straightforward idea that current and voltage can equally affect your power. So if you increase your voltage, it will increase your power. If you increase your current, it will increase your power. But they both increase the power in the same way, in other words, right? Whereas the next equation, V squared over R, tells us something about the relationship between voltage and resistance in increasing the power. So the first one, if you double your voltage and half your current, you can have the same amount of power. So it gives you an idea of that power relationship between current and voltage. But here, your voltage and resistance are not related directly, and one of them is squared. So this is telling us that voltage, if you increase your voltage, it really increases the power, whereas if you decrease your resistance, it doesn't increase the power quite as much. When you're just talking about the voltage and resistance in the circuit. And here, the most important thing about the power equals I squared R is that when you've got a resistive circuit, you've got current and resistance going on. When you have a resistive circuit and some current flowing through it, the thing that's really important when it comes to the power is what? The thing that really changes the power is the current, because it's squared. So if you really want to lower the power draw on a circuit, or the power used in a circuit that is a resistive circuit with a current flowing through it, you want to lower the current as much as possible, right? So these things are quite important. Reducing the resistance is not nearly as important as reducing the current. So here's an example. We've got an example with the two previous examples, actually. So we're going to find the power dissipated in the car headlight in these examples that we had before, where we calculated the power going through a tungsten filament and the resistance of a wire or whatever else. And we want to do it when it's hot and cold, because it's going to change when you turn on a lamp. At first, the filament is cold. And so it behaves differently than after it's been on for a while. After it's been on for a while, the filament heats up. Doesn't even take that long. A fraction of a second when it's hot. And then it's going to behave differently after that. So let's take a look. When it's cold, it has a particular resistance, and when it's hot, it has a different resistance. However, we happen to know that when it's a hot headlight, we have 2.5 amps from the previous example and 12 volts going through it. So that right there, we can calculate the hot power. So it's 30 watts of power when it's hot. When it's cold, though, we have a different resistance, so we're going to use this different resistance, which happens to be 0.35 ohms, and we're going to use that with the voltage, which we already know, 12 volts squared over 0.35 ohms, and calculate the power that it draws when it's cold, 411 watts. So when you turn on the lamp, it takes 411 watts of power to get it started, to get going. And then after it's going for a while, it slowly, well not slowly, but it quickly drops down to 30 watts of power. And what that really means is that it draws a lot of current through this small resistance while it's cold, and then as it heats up, it draws less and less current. Where do you see that? Where do you see evidence of that when you're turning on a light? Do you ever see evidence of this super fast power draw when you're turning on a lamp?
When it burns out.
Right, so when does a lamp burn out? Right when you first turn it on. Always. It's always, you flip it on and it goes, right? So why does that happen?
Because it
You're on the right track.
can't handle the power.
That's right. So over time, the filament degrades. The filament gets old. You get a little bit of oxygen inside your lamps because the lamps leak oxygen. Your lamps are usually sealed up with an inert gas inside, argon or some other thing, nitrogen. But if oxygen gets in there and you have a degraded lamp, a degraded filament, even if oxygen gets in there, it's going to oxidize the filament. And the filament will not have the right resistance, and it will heat up and it will get damaged and it will evaporate and it'll become less and less thick. You'll lose thickness of your filament essentially. And if that filament doesn't have enough thickness to withstand the heat, and you turn that on and it pulls 411 watts of power out of that socket, that filament can't handle that heat and it's just going to burn. It's going to pop, it's going to melt. And that's what you see. So eventually, these incandescent bulbs do burn out in that way. It's the same with other bulbs as well. It's the same with LED bulbs, and it's the same with these bulbs, except it's not the bulb that burns out in that case, usually. Usually it's the electronics driving the bulb that burn out. So they can have, the electronics can have the same problem, because they'll still draw all that power at the beginning, right? So cold electronics tend to suck power until they warm up. Here they calculate the power using a different method by calculating the current first and then using a different equation. And you can do that too, but from this equation you can see how many amps it draws. It draws 34 amps. That's a huge amount of current. Anything that's not milliamps or microamps is a huge amount of current. Anything that's an amp or more, I mean, in fact, 500 milliamps is even, half an amp is a lot of current. But most electrical devices use, like milliamps, microamps of current. It's not until you get in, like power tools and stuff draw amps of current. But now, we pay not for power, we pay for energy when we're paying for it at our house. However, it's a little confusing how they show that. On the outside of your house, your meter will measure your energy that you've used in kilowatt hours, which sounds like a power, but it's not, because it's watts or kilowatts times a time, hours. And since watts are energy divided by time, then watts times time will give you an energy. They just use they don't use seconds, they use hours. And so the kilowatt hours on your meter out there is measuring energy. If you want to know how many watts you're using, you'll have to look and see how fast the dials are spinning, right? And then calculate it from there. The faster the dials spin, you're using more energy per time, right? But it is a measure of energy. And then, in Nebraska, we're paying I think we're paying about 12 cents per kilowatt hour or something like that. Sounds about right. And that's pretty cheap. I think in California they're paying like 50 cents per kilowatt hour or more. But essentially what you do is you just multiply the kilowatt hours that you use, and by that, that cost, and you get your power bill every month. But other things are different. Let's see. So if you want to know how much you're going to pay to use a light bulb, for example, you have to take the power rating of that light bulb, which is usually right on the light bulb, 60-watt light bulb, for example, is a 60-watt incandescent light bulb. When it's fully powered, uses about 60 watts of power. But that doesn't tell you energy. You have to multiply that by the amount of time that it uses that power. And that has to be in kilowatt hours if you're going to use the 12 cents per kilowatt hour unit for paying for your power. So in this case, they take a 60-watt bulb burning for 1,000 hours, gives you 60,000 watt hours. You need to convert that to kilowatt hours. 60,000 watt hours is 60 kilowatt hours. And then you multiply by that 12 cents per kilowatt hour, and you get $7.20. And that doesn't seem like a lot, but it adds up. It adds up really quickly. This is why we use the new light bulbs, the LED light bulbs, or the compact fluorescents. The compact fluorescents are not nearly as good as LEDs, but the compact fluorescents were the only option before they could figure out how to make a really high power LED. Okay, now we move on to alternating current versus direct current. So this is the big, Nikola Tesla versus Edison, right? Versus Thomas Edison. Who was who? Who was the proponent of which one?
Tesla was alternating current.
That's right. Tesla was all about alternating current. Edison was all about direct current. Does anybody know why? What were their arguments?
Well, Tesla was somewhat promised, not really promised, a deal with Edison if he could design something that would work. And that never went through. And then,
Yeah, there was a lot of backdoor kind of
but then also Thomas
stuff going
Edison
on.
thought alternating current was too dangerous.
Yeah, so here's the argument. Direct current is this idea that you drive the current in one direction all the time, so that you deliver electricity by creating a high voltage. Creating not necessarily a high voltage, but you're creating a potential across a circuit, and then driving that current through that circuit in one direction, like we've been talking about so far. It's simple, number one, it's very simple, and to deliver it a very long distance, to deliver it, to run things with direct current, you don't need a very high voltage. You can run things with 12 volts. And 12 volts isn't very dangerous, because it's not, if you touch 12 volts, it's not likely you're going to get shocked, because your skin can resist that kind of voltage. Your skin, the dielectric strength of your skin is higher than 12 volts when it's dry. And so you could have a house that would be safe for, like sockets and things. You could stick your screwdriver in the socket and you're not likely to get shocked. And it would be fine. It would be a safer home for kids and everything else. The downside to direct current. Harder to make, yes, true. But that's not a huge deterrent. It is a deterrent. But harder to make it travel is even more of a deterrent. The direct current idea would require that you would have a power plant pretty much in every neighborhood, because that current can't travel very far without losing power. Why? Because of those power equations. The power that you lose going over a resistive wire is V squared over R. Sorry, V squared times R. No, I squared times R. Sorry, I keep getting the wrong equation. It's I squared times R. The current squared times the resistance. And at 12 volts, in order to run something, you have to have a fairly high current. So the current is high, the voltage is low, but it's the current that determines the lost power. So if you have a high current and you square that, then you lose a lot of power if you go long distances, if you have a big resistive wire. So that you'd have to have short wires so that you had small resistances, and you'd have to have power plants pretty much at every house almost, just in every little neighborhood you'd have a power plant. And what's a power plant? Well, a power plant is something that's converting essentially coal or oil, something burning, into electricity. So you'd have, smokestacks in every neighborhood. You'd have, and this is how Edison envisioned it. But, Edison lived during the Industrial Revolution. So smokestacks in every neighborhood were already a thing. They're like, cool, yeah, that's fine. Everybody's burning coal anyway. And they didn't think much of it. However, some people had a little more foresight. Some people said, you know what, we're going to get sick of living in a smoky neighborhood because we already are sick of it. And maybe this is going to be a big thing, a big deal. Electricity is going to be a big deal, and we're going to want a lot of it. So that's going to be a bad thing. Also, Edison lived in America, where there was a lot more space. He lived in New Jersey, which at that time, 100 years ago, was just open ground. I mean, there was Newark, New Jersey, and there was, there were a couple of cities that were crowded, but not many. Most of New Jersey just had open space everywhere, and so you could build anything you wanted. If he lived in New Jersey today, he wouldn't be thinking this way. But where was Nikola Tesla from? He was from Europe. He's from Serbia. Everybody's crowded in Europe, and it's been that way for 500 years. They've never had free open space as long as they can remember. And so they just had different modes of thinking. And so eventually it was Tesla that won out because there were some all kinds of business things involved and all kinds of political things involved, but really it was the better idea as well. With Tesla's idea, you don't use direct current, use alternating current, which is easier to make because in either case you're going to start off with alternating current. You're going to have to start with that, and then you're going to have to change it to direct current if you go to direct current. But with Tesla's idea, you can start off with the alternating current and leave it that way. You have to do some things with it, but the things that you have to do are not that hard to do. The one thing that you have to do is you have to raise the voltage huge, make it huge. So you create a power plant that's far away from a city, and you crank up the voltage to hundreds of thousands of volts. But in so doing, because of the power equation, P equals current times voltage, the current goes way down to almost nothing. If you jump up your voltage 100,000 times, then your current goes down 100,000 times. And that's great because now you have a super tiny current when you need to send it over the wires. You have a huge voltage, tiny current, you lose almost no power. It's beautiful. Then, as you're doing that, sending that super tiny current over these super long distances, you get to the other end and you can switch it back again. You can actually change the current to a higher current and the voltage to a lower voltage. You say, well, why couldn't we do that with? Why couldn't we just do that with the direct current? You can, but it's very difficult, and you lose a lot of power in the transfer. With AC current, you don't lose power when you change from current to voltage. You don't use very little power. And so alternating current just has all these advantages to it that were discovered, and it just made perfect sense to take advantage of all these great things. You can transport it long distances. It's easy to convert from high to low voltage, high to low current. The downside is that when it comes in the house, it is at a fairly high voltage, 120 volts in America. In different places, it's different. In America, technically, it's about 115, but it's different in other parts of the world as well. And so that is a downside because it is enough voltage to go right through your skin. So if you touch power in your house, you could get a little zap from it. You could even get killed from it. So it is a bit dangerous. You have to be more careful with it. But the upsides, I think, are more than the downsides, in my opinion. However, this does have this changing nature. What we're seeing with this alternating current is instead of going in one direction and just pushing this current around the circuit, it's like you wiggle it back and forth. You push it one way and then you pull it the other way. You push it one way and then you pull it back. And that is still electricity. Electrons are still moving, but instead of moving through the circuit in one direction and kind of pushing each other along, remember the domino effect we talked about? Instead of this domino effect just going one way, it goes one way and then it goes another way. It goes one way and it goes another way. And we do it at a fairly high frequency. 60 hertz is what we use here in the United States. Other places use 50 or 40 or 80 or whatever. But we use 60 hertz, which is 60 times per second. This is going back and forth. And why do we use 60 times per second? One of the reasons we use 60 times per second, one of the biggest reason I think we use 60 times per second is because the human eye can only perceive things at about 20 hertz. At 20 hertz, we start to see things vibrating. You go much faster, much higher than that, then our eyes can't perceive it. So if we if we had our power going at 10 hertz, for example, we would actually see the flicker and it would drive us crazy. At 20 hertz, we would perceive it, our brains would recognize it, and it would drive us crazy. At 60 hertz, our minds can't really perceive it, and so it doesn't bother us. Some people can perceive it. And at 60 hertz, sometimes it can cause people to have seizures. Some people struggle with that. So some for certain frequencies for certain people causes problem. But for most people, 60 hertz is not a big deal at all.
So is that why when a light is starting to die, it flickers?
No. When it's starting to die, it flickers usually because the filament gets broken and it opens, but then it kind of wiggles and it goes tap, 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 tap. And it flickers that way. It's just, it's the bulb is dead, but it tries to get alive again. That's why it flickers. Also, some bulbs, many bulbs actually, are made with multiple filaments. And if one of your filament breaks and it keeps touching, then it will go bright, dark, bright, less bright, bright, less bright, as one filament does that. Many bulbs, especially high quality bulbs, are made with multiple filaments so that if one breaks, it will still work. So, all right. So how do we talk about this stuff mathematically if it's changing all the time? Well, of course, we make a function that changes. We use a function that changes all the time, and that would be a periodic function like the sine or the cosine. And we're going to start off with the sine to represent the voltage change. So if the voltage is changing all the time, then we can use this function here where V0 is the maximum voltage or the peak voltage right here in this wave going back and forth, positive to negative voltage, positive to negative voltage. And the sine shows you how much it's changing. So that tells you how fast it's changing essentially. You take the sine of 2 times pi times f. Those are all constant terms. The 2 and the pi, of course, are constant numbers. The f is the frequency at which you're going to make this thing roll. So that would be 60 hertz in American households. And then t is the time in seconds. So if you plug in a time in seconds into this function, it'll tell you exactly what the voltage is at that time. Since the voltage is constantly changing, you have to have a function that changes to tell you that voltage at a particular time. So that's the first function that we use. If that is the case, then the current will change in sync with it, as long as it's designed to do so. It turns out that you can actually have a current that is not in sync, it is out of phase in different ways because of the circuit that it's being used on. But if it's just going through a normal resistor, then if the current is just being driven through a normal resistor, then when you raise the voltage, the current will raise with it, right in sync. So in a very simple circuit, then this is your voltage function and this will be your current function. And it's the same essential function, except you replace the V naught with I naught and the V with an I and you're good to go. But how are we going to calculate power? Power is I squared R, or V squared over R, or I times V. And when you multiply those things together, you're going to get a squared sine function, right? You're going to get a sine squared function, and sine squared is still a periodic function. It goes from a 0 power up to a maximum power, down to 0 and back to a max. So it's the power, in other words, is changing all the time in a alternating circuit, alternating current circuit. Well, what we do is we take a kind of an average. It's not exactly an average. It's what we call a root mean squared average, and it's a calculus thing. But in the end, it does look exactly like the average for power here. You get 1/2 times the current times voltage instead of just the current times voltage. So you take the maximum current and the maximum voltage multiplied by 1/2, and it gives it to you right there. So that makes sense. This one may not make sense though, because when you take the root mean squared of just the current, or the root mean squared of just the voltage, you don't get a normal average. You don't get the average that we're used to. So the average current in an AC circuit is actually the current over square root of 2 instead of just current divided by 2. And that's because if you take the average of the sine curve, you get 0, don't you? And if you take the average of the cosine curve, you get 0. And so we take a different type of average when we do that, and the root mean squared of this gives you the current over square root 2 or the voltage over square root 2. And whenever you're calculating the average power using current times voltage, that's what we do. We use the root mean squared and the voltage root mean squared, and that will give you that current times voltage over square root 2 that we just saw. Sorry, current times voltage over 2 that we just saw. So these equations are valid. The power average here is valid. The current root mean squared, which is the average current, is valid, and the same with the voltage. That's valid. And that usually is, when we talk about the voltage coming into our house being 115, that is the root mean squared voltage. That's what we're talking about. Whenever you talk about the voltage or the current in a AC circuit or AC system, we're usually talking about the root mean squared voltage or the root mean squared current. IRMS, VRMS. So that is just your very quick version of how to deal with AC current. Let's do an example using some of these equations. What is the value of the peak voltage for 120 volt AC power? So this 120 volts is the root mean squared, or the VRMS. So we plug that in for VRMS into our equation right here and calculate V0, which is the max. I don't know why they call it V0 and not Vmax, but they do. Anyway, solving for that, you get Vmax equals square root 2 by square root 2 times VRMS. I'm going to lose my voice here. And plug in the numbers, you get 170 volts. So it's actually going from 170 to negative 170, back and forth to give you that 120 average voltage. And we're going to calculate the peak power, which is the peak current times peak voltage. So if you calculate the peak voltage, peak current as well, let's see what they're doing here. Equivalent DC voltage is constant 120 volts. Oh, they do this by saying that we know the average power is 60 watts. So in other words, they want to know the peak power. So the peak power, if this is the average power, and if the average power is 1/2 I naught times V naught. Yeah. Well, not initial. This is max. These are max voltage, max current. And if this is your average power and the total power, the max power is twice that, then you just take that power that they give you as the average power, 60 watts multiplied by 2, and the peak power is 120 watts. So it's just a matter of understanding that what the numbers that you get for power and current and AC current are not necessarily, and voltage, are not necessarily the peak, they're the averages, right? So that's the goofy thing though, is the I0, V0 doesn't mean initial, it means peak or maximum, which I think is confusing as well. So here they actually describe a little bit how AC power is used. They use these things called transformers to raise the voltage and to lower the voltage so that they can distribute the power very long distances. And here we're going to do some math concerning that. We want to know what current is needed to transmit 100 megawatts of power at 200 kilovolts. So this takes advantage of this equation here, power average equals I RMS V RMS. And they're going to transmit 100 megawatts of power, so that's our power, using 200 kilovolts of voltage, and they want to know what is the current. So we plug in the power and the voltage and solve for the current. Current equals power over voltage. Plug in those two numbers they give us, and it's 500 amps. Now that's a ton of current. That's a lot of current, but it's a very small amount of current compared to what it would be if they didn't raise the voltage up to such a high voltage of 200,000 volts. So at 200,000 volts, you have 500 amps, and the power that you're going to lose if you put it over a power line is going to be I squared times R. The resistance is going to be 1 ohm. So they're going to have 1 ohm of resistance on their transmission lines. And so the power loss is going to be the 1 ohm times the 500 amps squared, which is 250 kilowatts. That's not bad. Remember, their original power is 100 megawatts, right? So this is not even a fraction of a percentage of that. In fact, it's 1/4% power loss. That's not bad at all. If you lose 1/4% of your power transmitting it, you're happy. Especially because you're paying, I mean, you're charging per watt, right? So if you're losing 1/4%, hey, that's not so bad at all. So that's the reason they do that. If they didn't raise that power up to 100, or that voltage up to 200 kilovolts, if they had to keep it at the voltage that it comes off the generators at, and the voltage coming off of a generator is, I'm trying to remember here, it's probably in the hundreds to thousands of volts, so at least 1,000 times less, or hundreds, well, at least hundreds of times less, then you would have hundreds of times more loss. So instead of 1/4%, you'd have 25% loss. That's significantly worse. You probably wouldn't even make any money at that point. So 100% difference in your profit margin, that's not bad. Or I mean 100 times difference in your profit margin. Not bad at all. All right. Now the last two sections of this book are, this next session is about electric hazards. And we've talked about those a little bit, so we'll review them again because they are important. So the two kinds of electric hazard are shock hazard and cooking hazard, right? Shock hazard is this idea that if you have a high enough voltage, it can go through your skin and shock you. And it doesn't take much current to flow to be damaging. I mean, it's just a few milliamps, I think, that'll stop your heart. So it doesn't take much current. If you have a high enough voltage to get through your skin, just a little bit of current going through you can stop your heart. It can be bad news. But thermal hazard is where you get enough power going through your body. So you have high enough voltage to get through your skin, but also a current that's high enough that it will literally cook you. It will literally cook your flesh. And then, I mean, cooked flesh is absolutely irretrievable by your body. Cooked flesh has to be cut off. And that's why it's dangerous. Okay? So not only cooked flesh, but cooked bone also has to be cut off. Your body cannot recover from that. It's worse than frozen flesh and frozen bone. Your body can sometimes recover from that. So anyway, those are the two electrical hazards, and this is why electricians only work with their right hand, keep their left hand in a pocket. This is why electricians only work on fiberglass ladders, because it separates them from ground, so that electricity will not try to go through them to get to ground. Then oftentimes when they're working on a ladder like that, they will have their tools grounded to the ground. Sometimes they're working with tools that actually have cables connected to them that are connected to ground, depending on what they're working on. And Scott, I'm sure you do a lot of this out at the railroad. A lot of grounded tools, a lot of ungrounded workers, isolated workers, because they're working with high voltages. What are some of the voltages on the engines out there?
Our secondary for the control system, I think, is right around 600. It drops down to 15 volts, 72 volts DC.
So you've got two different circuits there. One at 600 volts, one at 15 volts.
Well,
that's a huge difference in voltage.
There's three, because then you have the traction motor from the main gen. It'll put out close to 3,000 volts at 3,000 amps.
So this is a different idea, but it's the same thing. It's the voltage difference that matters. It doesn't matter if it's a high voltage. If it's 20,000 volts, but the only thing around you that's a different voltage is 19,999 volts, that's only 1 volt difference. No big deal. This is why a bird can land on a 20,000 volt wire, because the voltage difference between their 2 feet is so tiny, it doesn't matter. However, if the bird lands on the wire and sticks 1 foot on the ground, they're dead. Or if they put 2 feet on different wires and there's a difference of voltage between those wires of 10,000 volts, that bird is going to explode, literally. Okay? And so if you're working on a circuit on that rail car and it's 600 volts on one and 15 volts on the other, that's almost a 600 volt difference. It's going to travel through your skin. Okay? And then the current that goes through will either stop your heart or cook you, depending on how much current is going through, how much current is available in the circuits. So yeah, I mean, that's the same deal. So when they're working on those circuits, they either protect them from touch or they might ground them in some way so that the current goes a specific way and has a path to go to. Because if you give the circuit, if you give the electricity a good path to go to, it will choose that path most of the time. And it won't choose you.
Yeah, people aren't very good.
Not very good conductors, yeah. Unless their hands are wet. Which is another thing, you know. If your hands are wet, if you've just gone to the bathroom, you should not work on electrical circuits. You should wait for your hands to dry really good. Or wear gloves. So yeah, there's a lot of things, a lot of important things about electrical safety. Now, one of the most important things about electrical safety is building electrical safety into your electronics. So one of the things that we do is we make fuses. And what a fuse is it's like a little light bulb that if it draws enough current to be dangerous, it burns out the light bulb and cuts off the circuit. So if it's starting to draw enough current that it starts to look dangerous to a human being, it essentially burns out. And so here's an example. You have a toaster that's designed to pull a certain amount of current. Let's say this toaster is designed to pull 5 amps of current. That's pretty reasonable for a toaster. And so you turn on your toaster, it draws 5 amps, and it toasts your toast, and that's fine, you turn it off. But you can build into this toaster a resistor, which is like a little light bulb, that if it draws more than 5 amps, let's say if it draws 6 amps or 7 amps, that filament inside that light bulb, which we call a fuse, gets so hot it melts. Then it cuts off that circuit. And you put it there, you put it in the line with the wire so that it just cuts off the wire. It essentially just closes that, opens that circuit. And that's what we call a fuse. And there are some fuses that act slowly, some fuses that act extremely quickly, usually ones that are for safety for a human being, act very quickly. So that if that current changes, it just pops. And those fuses are extremely useful for protecting the equipment and for protecting the users and for other reasons as well. But they're pretty simple devices, and just these very simple fuses. Then there's another kind of device that we often use, and you've probably used these in your house without even understanding how they work. But these are called breaker switches. Thank you. The reason they're called a breaker switch is because they break a current, they break a circuit by opening the circuit. Essentially, they use the same method or the same physics. Essentially, they use heat, the heat of a metal, but instead of it breaking the metal or melting the metal, it bends the metal. Remember last semester when we used this device and we bent the metal? That's the same device that's used in a breaker switch. In a breaker switch, you have the current coming in onto this bimetal strip, which is what this is. And as this bimetal strip has current going through it, it heats up. But if it heats up enough, it bends enough for it to slip into this little notch here. If it slips into this notch, this whole thing bends downward. This whole thing comes downward, and it disconnects from this little contact. Actually, this contact here. It disconnects from this contact, so that when this thing gets too hot, the circuit opens. So if too much current is flowing through one of the outlets or one of the parts of your house, that thing bends and bends and bends and then it pops open. And it permanently stays open until you literally go back and hit the switch. And if it's still too hot, you can't open it. You can't close it, rather. You can't, the switch won't close. It'll just pop open immediately again. So this allows you to have, and this doesn't act nearly as fast as fuses can, but it allows you to reset it without having to replace the fuse. So those are kind of nice to have at the main of your house, these circuit breakers. And they do make faster acting ones and slower acting ones, but they're limited because they're such a mechanical device. If you really need safety, you need to have it right at the point of contact. Now the faster acting ones are in bathrooms all the time. You see them as GFCI switches. They have been able to make fast acting. They've been able to make fast acting circuit breakers, but they're not standard. They're not like this. They're not a mechanical circuit breaker, from what I understand. They're actually what we call a solid state device, which uses kind of essentially uses a little microchip to open the switch, so that it can open it much quicker. So those ones you see in your bathrooms and your kitchen that have the little push buttons that you have to reset every once in a while, those are called GFCIs. They're really quite expensive, at least $5 an outlet, sometimes as much as $20 an outlet if they're faster acting outlets. But they can protect, they're fast enough to protect humans, and so that's why they put them in there. Back in the day, if you've ever watched old movies and seen people, when they lose power in their house, they have to actually replace the fuse. They actually had to pull a fuse out and put a new one in. Christmas Story comes to mind.
Yeah, that's what I was thinking.
So in a circuit, a fuse or a circuit breaker looks like this. It has two open dots with a little curly Q in between to represent that filament in the fuse. The fuses and circuit breakers look like this. Here they show you what kind of currents cause what kind of things, what kinds of damage. So at 1 milliamp, you can feel it, but it won't hurt. 5 milliamps is the maximum harmless current that can go through your body. So if it actually enters in through your skin, and if it actually gets in there, 5 milliamps is the smallest you can feel without any damage, without any harm. 10 to 20, sustained muscular contraction. So if it's DC current, and you get 10 to 20 amps of DC current in your hand, for example, it will cause your hand to contract. So if you're grabbing something, if you're holding a wire, it will cause you to grip it. So you won't be able to let go. If it's AC current, it'll cause you to grip and then let go, and grip and let go at 60 hertz. So it'll pretty much be just like gripping it again, because you won't be able to, your muscles won't be able to react as fast. Regardless of what it is, AC or DC, you're going to be hanging on to something, or your muscles are going to contract. It could cause your toes to curl up, or your mouth to clench. Muscles are going to contract, right? Of course, if it goes through your chest cavity, the muscles in there are a problem if they contract, right? If your muscles in your chest cavity contract, it can squeeze all the air out of your lungs. Because when your diaphragm contracts, it exhales. Exhaling is contracting. Relaxing is breathing. So that's not good. And it could stop your heart. I mean, it could cause your muscle to contract. So it could cause a defibrillation, which is not good, right? At 50 milliamps, you're going to start to feel pain from those contractions and from other things. And then you can get definite fibrillation in the heart at 100 to 300 milliamps, right? And then at 300 milliamps, you start getting cooking, you start getting burning, particularly on the surface of your skin. And then at 6 amps, right, nothing is gonna make it out of that, right?
On the other hand, at 6,000 amps, you can start.
That is true for a very short time. If you go for a very long time, you're going to cook your heart. So it's very short bursts. At 6 amps, you can, that's where you get definite defibrillation. So you can definitely make things happen. So here they show a nice little electric arc between two wires. That's essentially two wires that have enough voltage across them, enough voltage difference between them, that they're ionizing the air in between and the electricity is traveling through the air in between, right? And is it dangerous? Well, it just depends on what that voltage difference is, if it's enough to travel through your skin, and how much current's flowing, right? And that also depends on the frequency. Those things depend on the frequency because right here they talk about how the frequency affects. Oh, it's right here. How the frequency affects your body's response to electricity. So if you have a very low frequency here, you have you can feel it, but you're not necessarily going to have a problem with, for example, not being able to let go. At lower frequencies, you have a better chance of being able to let go because your muscles aren't contracting and relaxing at such a high rate. And that's why we use 60, because look how low that is. At 60 to 100, you have the lowest problems with letting go of something if you're electrocuted. Right? It still can be a problem, but you have the lowest problems at that point, particularly at these low currents. However, as you go up in frequency and up in current, you have problems. You have problems where you actually cannot let go at all. So frequency matters with danger and with the dangerousness of, or the danger in circuits, I suppose you call it. Now we go on to some biological, discussions. Essentially, what nerves do is they create a potential difference across the nerve using some biochemical processes. And you have one end of the nerve here, which is where the nucleus is, and this long tail in between. This is not to scale. This thing is much longer than it would be. This would be much longer in the body than it is here. But this end of it, that has these little nerve endings, can be connected to a muscle, but it can also be connected to another nerve. So all of the nerves in our bodies, all these neural pathways are just one nerve after another nerve, one end connected to another. And they create these voltages, and these voltages allow the nerve impulses to travel. So they go from one end of a nerve to another end of a nerve cell, and just keep traveling because these voltage differences that are created in these biochemical processes. Quite interesting. Another biological application of this is, I think we talked about this, but I don't remember. But anyway, is the idea of, what do they call this? Where you have osmosis. Kept thinking mitosis and meiosis, but that's like reproduction and stuff. So for osmosis, as when you get molecular transport through a membrane, right? You get salt traveling through a membrane, water traveling through a membrane, whatever else. And it all has to do with really concentrations of ions on either side of that membrane. If you have a higher concentration of salt on one side of a membrane than on the other, then the higher concentration of salt on one side versus the lower concentration on the other is going to create a potential difference. The ions create voltages. They create potentials, and it'll be different on either side because the concentration is different. So you have a voltage through this membrane, and that voltage drives this transport. Essentially, it's like an electron in an electric field, or in a potential difference. It's going to push these different molecules through, or pull them through one way or the other. They'll be attracted one way or the other, and if that attraction is strong enough, they can go right through the membrane. It's a Coulomb force thing.
within the brain, there's just countless things that happen in the brain. It's just so many crazy things, and they talk about that here, the different fats inside the brain and the neurons and all kind. I mean, it's just so many different things that you can talk about. Electric eels, right? Electric eels are very cool because they use this fact that the neurons, all the nerves in your body create these electrical impulses, and they've got these muscles along this long eel's body, and they flex their muscles in a very specific way so that they get a very low voltage on one and a very high on the other from their neurons. And then if they're near an animal that touches them, that voltage change shocks them. It's beautiful. I mean, if we could learn to flex our muscles in that way, we could be an electric eel too.
We could have electrical artists.
We could. We could. There's no reason why we couldn't do it, but we've not evolved in such a way that we can flex our muscles that way. We have all the building blocks. Maybe that can be a superpower. Somebody can learn how to do that and become a superhero or a supervillain.
Somewhat realistic.
But we actually do it without even knowing it. And when you go in for an electrocardiogram, when somebody's monitoring your heart in a hospital, that's exactly what they're doing. They're measuring the voltage differences across your heart. And that's what you're seeing on those peaks on the electrocardiogram. One peak is as one muscle contracts and creates a voltage difference, and then another peak is as another voltage contracts. Some of those voltages are positive, some of them are negative. Some of them are big, some of them are small. And the doctors know exactly what they should look like. That's why they can look at that heart monitor and say, your heartbeat is regular. Or they can look at it and say, it's irregular. It's not, the peaks aren't spaced properly, or the peaks aren't the right size relative to each other, or whatever else. So they're just looking at voltages, essentially. And this is why when you're doing pre-med, you have to learn this science, because you're going to learn more of it later. You're going to have to apply it later. In fact, so much monitoring so much of the monitoring done in the medical world is done by monitoring voltages, currents, magnetic fields, electric fields, so many different things. They monitor breathing by monitoring a magnetic field and a current. They monitor oxygen by monitoring light diffusion, which is essentially electromagnetic waves. I mean, so many different things. Blood pressure is monitored by monitoring a current flow and a change in magnetic field. So here we have a blood flow monitor, and we have the heart monitor. So anyway, so many different things going on. On the bottom of this section, you see all these monitoring devices, and they're electrodes. There's one around right the lower rib cage of this astronaut. The reason that's wrapped around the rib cage is a very, very specific reason. The actual wrap, the strap, is actually a wire. There's a wire inside of it. And so there's a current going around the rib cage. And as that current goes around the rib cage and you're breathing, as you breathe in, your rib cage expands. So it changes the length of that wire, the length of that loop. And the changing of the length of that loop actually changes that circuit in such a way that they can measure the breathing. So everything is just indirect measurements of circuits and electronics and other things. It's to the point that almost every single medical device used in hospitals today, almost every single one. There's like the stethoscope, and that may be the only device they use in hospitals that was not invented by a physicist. That may be the only one that was invented by a doctor, okay, by a medical doctor. Almost every other one was invented by a physicist, including X-ray machines, MRI machines, everything on the imaging department. Blood pressure, cuffs, everything. All those things invented and developed by engineers and physicists, because it is all engineering and physics. That's all it is. Well, I mean, you can make argument for some things that are, you know, fairly biological, but I mean, and we don't usually consider pure biological things to be physics unless we're looking at the very fundamental physics of them. But it's just interesting to go in. It's really interesting to go into a hospital for me, because I look around and I say, oh, I can understand that. That's physics. I can understand that. That's. I have no idea what the doctor's talking about half the time, but I understand how he's getting his data, because it's physics. It's cool to me. So anyway, that's the end of this chapter. I do believe. Yes, it is. So we are on to
I'm
chapter.
looking at these questions.
Yep.
I think you need to limit it to about 15,
How many questions are
like 30.
just go through?
Excuse me. Let's take a look at the homework for today and see if you're. Let's see if you're right, or if we're good to go. So we have a rechargeable battery, and this little chemistry equation tells us that we get 1 electron from every lithium atom, right? So if we're using 83 grams of lithium, we want to know how much charge the battery can deliver in coulombs. So for 83 grams of lithium, you go up here to lithium, and it tells us that for every gram of lithium, for 6.9 grams of lithium, you get 1 mole. So have you guys taken chemistry? You've taken chemistry, no? You've not? Have you? Do you remember moles?
I know what it is, I don't remember it.
So lithium has a molar mass of 6.63, was it? On the periodic table, there's a number up there, and this one is 94. 6.94, and that means that for if you have 6.94 grams of lithium metal, that means that's approximately equivalent to 6 times 10 to the, what is the mole? 3 times 10, 6 times 10 to the 23rd? Yeah. 6 times 10 to the 23 atoms of lithium. So 6 times 10 to the 23 atoms of lithium has a mass of 6.94 grams. That's what that means. And here they're saying that we have, and they actually tell us
You gotta take that grams and change it to kilograms.
no, in this case we don't, because we're not looking for kilograms. We're not going to use the kilograms. We want to know how many atoms we have. And so here they tell us it's 7 grams per mole in this question. So we take that 0.83 grams of lithium and say, if I have 0.83 grams of lithium, and lithium is 7 grams per mole, and I want to know how many moles I have of lithium. So how do I do this? I look at this and I say, well, if I divide 0.83 grams by 7 grams per mole, that's going to give me 0.83 divided by 7, and the grams will cancel, and I'll have 1 over moles, that'll be moles. So that tells me that I have that many moles. 0.83 divided by 7 is like, whatever. It's like 0.1-ish. I don't know. It's not, it's like 0.12 or 0.13 or something like that. So that means I have 0.13 moles, or whatever it is. And then I multiply that by this number, and that will tell me how many atoms I have. Then that tells me this equation up here tells me for every atom I have 1 electron coming off. So then I multiply that number of atoms, because it's the same for the number of electrons, times the charge of the electron. And that'll tell me exactly how much charge I can get out of that much lithium.
1.6 times whatever.
Yeah, so I take my 1 point, did you say it was 1.6? If this thing equals 1.6 or 1.
I'm talking about how many charges per electron.
Oh yeah,
There's a
so,
lot of moving parts here, I don't understand.
okay, so let's go ahead and do this. Just go ahead and do this
Can
problem.
you print off my
You know what?
Can you print it off for me?
The homework?
Yes.
Yeah. I can't do it from here, but I can do it next room. You want to do it right now?
Yes, please.
Sure. Do you know how to do it?
Oh, yeah. No, not really.
You're not wearing shoes. I think it's kind of.
I'm going to go ahead and end this recording right now, though.
Okay.
We're done with discussing this chapter for now.